Hey everybody, we're going to do a little pre-video on resampling methods. So resampling is widely used in statistics and it's widely used in machine learning. The basic idea of resampling is that what we're going to do is we're going to take a limited chunk of data and we're going to randomly resample it. Randomly take either a permutation or some subsample or something like that from the original data. And we're going to use that resample in order to make an estimation. Now, doing this repeatedly, in the case of, for instance, a Monte Carlo simulation, is going to give us the ability to estimate what would be a truly random thing. Or doing it in the case of cross-validation will enable us to make a better estimate of how good a given machine learning system is actually performing. So these fundamentally are about getting estimates from a limited sample and increasing the ability of our estimate as compared to just using the sample raw. Oftentimes in the case of things like cross-validation, they're about making better use of a limited sample size, but they also are fundamentally like as if we are doing an experiment and we're observing an empirical distribution when we're talking about stuff like a Monte Carlo. Okay, we're going to get into this. Just know that, of course, there are downsides, right? If you could just get more data, that's probably a better idea. But oftentimes we can't. And well, because what we're doing with resampling is we're doing the same operation repeatedly, well, obviously it's more computationally intensive to do it this way. And maybe that doesn't matter if what you're fitting is in linear regression, which takes you, that long to fit. But if you're doing a giant neural network that takes about 5 weeks to fit, well, you probably don't want to do an awful lot of resampling with that. Okay, let's kind of talk a little bit about what the ideas of resampling are. So, especially if you've already taken COGS 108, you'll have seen the idea of Monte Carlo simulation. What is it? Well, what we do with Monte Carlo simulation, by the way, the name is that famous city in Europe that's known for being the Las Vegas of Europe with lots of gambling, right? Monte Carlo. And the gambling thing, the rolling dice repeatedly using randomness, that's what we're doing with Monte Carlo simulations. So Monte Carlo simulations mean we have something that we can randomize about our process. And we can do that repeatedly over and over again using a different random version of the original and compare those distribution of our randomized things and check that versus our original. Okay, maybe it's better if I just demonstrate that. So let's say we have, some treatment group and a control group. So these are the people that got treated by a drug, and these are the people that are controls, that they got sugar pill, right? So we have these measurements, and if you calculate the difference between the mean of the red and the blue, well, you get this value 10. Now your question is that value 10 actually important? Is the difference between those two means actually a real difference? Or is this just random chance? And if I did this experiment again, the next time, that value would be 0, or the value would be -3. Well, we can't do the experiment again. That's the basic idea here. We don't have that ability. But we can run a virtual experiment. The virtual experiment in a permutation test is to make permutations of this data. What if we took this data and we reshuffled it? If we just removed the labels treatment and control, and we just made a big old list of numbers, right? So those list of numbers are 58, 69, 64, 55, 51, 41, 51, 71, 42. And we make a random set of labels for it, okay? So I'm gonna label this one red, that one red, that one red, that one red, and I'll make these ones blue. Okay? Where the only thing I'm doing is I'm maintaining the overall proportion of red and blue samples. And what I do is I can test by this random labeling of the real data, permuting the labels, right? I can make a new difference of means, and I don't know what this is, but like, let's say in this case, the value is -3. Okay? This is the value of the means. So I can do that once, and I can do that again and again and again. And every time I create a random permutation of these original labels, what I can do is I can drop that particular difference of means into a histogram. And as we build this histogram, what we can see is we're making a distribution of, hey, what is the null hypothesis here? The null hypothesis is there's no difference between treatment and control. Well, if that's the case, I can shuffle the labels and create a distribution of, hey, how wacky would it be to have a value that is the true actual value that I had in my difference of means, 10, right? How unlikely is it for that to happen given this histogram that I see here before me? Well, in this particular case, that p-value is 0.06, so we didn't reach our magic number 0.05, so we can't say that the difference between treatment group and control group is truly significant, right? By the way, if you haven't ever heard me say this before, p-values, and especially p-value equal to 0.05 as a magic threshold, that's some BS. Do not ever use hypothesis testing as it is significant less than 0.05, and it is not significant if it's 0.06. That is not the way you should be doing statistics. If you want to hear more about that, come talk to me. But you should never just say significant, non-significant. You should always report a p-value, and you should understand that p-values are not what people think they are. This is not the probability of getting something this unlikely. Okay? It's different than that. Keep that in mind. Not enough time here to go into it. Okay. So, regardless, what you get is a p-value, which does estimate how we should view this particular experiment. Is this value of 10.3 something we should think is a real true difference or not? Okay? And while you should not use p-value as a magic threshold, it is a kind of evidence. All right. This is resampling using permutation testing. Again, what is a resampling technique? We take the data that we got, we produce a resampling of that data with different labels, and we do that again and again and again and again, right? Each one of these representing another resampling of that data. And then we look at that. The result from that, it gives us a histogram, and we can make a determination using a p-value to look at whether this is a likely or an unlikely event. Okay. You also, if you took COGS 108 with me, you saw this exact same technique on this exact same slide, right? Is the distribution of Walmarts in Massachusetts completely at random, completely spatially at random? Are Walmarts located at random locations or not? Well, what if Walmarts really were located at random? Here are the dots of all the Walmarts in Massachusetts, at least at the time that this slide was made, right? What we're going to measure is, we're going to measure the distance between nearest neighbors, okay? So that's the distance from that one to that one's nearest neighbor, right? This is the distance from that one to that one's nearest neighbor. That's the distance from that one to that one's nearest neighbor. So if we keep building up the nearest neighbor distances for all possible pairs of nearest neighbors, and we plot the average distance to the nearest neighbor, right? So I shouldn't say plot. When we measure the average of that, well, the true average is whatever this is, like 13,500 meters, okay? Well, if we think that Walmarts are not located anywhere in particular, if our hypothesis is that they're just dropped down in random locations throughout the state, then our null hypothesis is that they are distributed randomly. So if they're distributed randomly, that means we can do a Monte Carlo simulation. We can roll the dice. We can make a fake Walmart map and just dropping dots randomly anywhere in the state. Okay? And we can do that and we'll get, say, that measurement. And then we'll do another random set of dots and we'll get that measurement. And then we'll do another random set of dots and we'll get that measurement as the average distance. We do that repeatedly 10,000 times and we build up a histogram of an empirical distribution. It turns out that the real measurement of average distance to the nearest neighbor in Walmarts is here, and that enables us to calculate a p-value, which says that, yeah, we can't really separate the observed Walmart distribution from a completely spatially random process. Okay. Carriage return line feed. Another set of resampling techniques that we should talk about are ones that are specific to machine learning. Those last two are good for hypothesis testing, which we will be concerned with at a later date, okay? But something we'll be concerned with immediately is using resampling of the data to get a better estimate of performance, okay? So this technique, the bootstrap, is also known as resampling with replacement. We're going to encounter this in the not too distant future in machine learning world. So the idea of the bootstrap is you reach into the bag of possible data samples, you pull out one, but after you record that as being our data sample, you throw it back in the bag. It's replaced. So now we reach in the bag and we randomly pull out green sample, throw it back in the bag. Notice green sample is here. This time, hey, we pulled out orange sample a second time, maybe even a third time. When we do bootstrapping, when we do resampling with replacement, then the same data sample can come into the permuted data set multiple times. Okay? So in fact, if you want to, you can realize that that also means that some data samples in the bag are probably not going to get chosen at all. You know, if you're getting repeats, if you have a data set of size 10 and you pull out 10 samples with replacement, some of those 10s will be repeats, most likely. And that means some of the samples never made it out of the bag at all. So since the probability of choosing a sample is 1 over n, then the probability that something's not chosen, where n is the number of data samples, is going to be 1 minus 1 over n. That's the probability a single sample is not chosen, to the nth power. That's roughly 1 over e, at least as n gets big it is, and that 1 over e is 0.368. Okay, so that means that in large samples, any given particular data sample has about a 36% chance of not being chosen. So obviously the probability of being chosen is 1 minus 0.368. Okay? And so as n gets bigger, this asymptotically approaches that 0.632, the probability of being chosen, of any one given data sample being in there. Okay, this stuff becomes much more important when we talk about ensemble learning and random forests, setting you up for that. Okay, but this is important today. So another resampling technique, and the reason why I went through all this in the first place was to help you realize what cross-validation actually is. You've probably done cross-validation in COGS 108, right? But guess what it actually is? It's a resampling technique. It's a little bit like a permutation test. So what do? Just a reminder for those of you that have seen this before, or showing those a couple of you who've never seen it at all. If we have a limited data set, instead of doing something like dividing it up into a training set and a test set, well, what we can do is we can divide it up into multiple folds. So we have, in this particular case, 5-fold cross-validation. We will oftentimes note this as k-fold, where in this case, k equals 5. Okay, so this is k-fold cross-validation. We divide our data set up into 5 chunks. Importantly, I want to make clear about this, these data points are totally random. Okay, so like this data point over here ends up in this fold, this data point over here ends up in that fold. We randomize stuff. Why do we do that? We randomize because it's entirely possible that maybe, like, this is the January data over here, this is the February, that's the March. And it's entirely possible that whatever we're looking at is maybe a little bit different in June than it started in January. And if it's a little bit different in June than January, well, we need to make sure that we mix up the folds of the data. Otherwise, our estimates, like if we, instead of doing all this, right, if instead we'd done stuff like this, we would have folds that had very different properties for our learning system, and that's not good. Okay? So this is our situation. We randomize things into folds. And what we do is we make repeated cross-validations. So every single fold gets its turn as the test set. Okay, right now this is the test set. And everything here, folds 2 through 5, are the training set. So we train our machine learning system on this. We get its performance level on the test set. Let's say it's 38.7. Okay, now we do this again. We take our same machine learning system. Now this, fold 1 and folds 3 through 5 are now my training set. It's fold 2's turn to be the test. So we train on the green stuff, we test on the blue stuff, and maybe what we get is that as our performance metric. We do it again and again and again. Okay, now our actual estimate of performance is going to be the mean of all these scores. And that's cross-validation. So however many folds we divide up the data into, that's how many training and testing cycles there are. Note, each one of these splits is a resampling of the training testing procedure. Note that every single data point in the data gets one and only one turn as the test set. Every single data point gets k minus 1 turns in the training set. Okay? So yeah, this is all resampling. The idea is that we can use permutation tests, for instance, to estimate if model 1 is really better than model 2, or is it just by chance? And in doing so, we're making simulated runs by relabeling the outcomes, okay? We don't have to actually make real runs. In bootstrap sampling and cross-validation, what we're doing is we're actually making runs of the machine learning system. And what we're doing is we're permuting how the training and testing set work in order to reuse a limited amount of data to get a better estimate of the metric. If you have giant internet-sized amounts of data, you would never use bootstrap or cross-validation because it's computationally intensive. You've got enough data to not care and just get an estimate of test set performance by just using the test set. But when your data is limited, this helps you reuse that limited data to get a better estimate. Okay, that's all I had for you. See you in class. Bye.